Today's notes are the first day on a series of days we're going to do about a topic called factoring. Today is going to be an introduction and reminder of some stuff that you hopefully already know and kind of setting us up for success in future days. So before we get into the notes page, I want to just talk a little about what factoring is and what it means. So you've seen factoring before. You probably have taken numbers in earlier grades and broken them down into like smaller numbers. So maybe if you have the number 20, you could express that as factors of 1 times 20 or 2 times 10 or 4 times 5. So each of those is a pair of factors that create 20. And the idea is we can divide each of those out of the number and we'll be left with another integer as the remainder. So we also used factoring this year. So these are called factor pairs. And we will be using those pretty soon. But so far this year we've done prime factorization. And in prime factorization, we were working with simplifying radicals, and we had something like the square root of 84, and then we simplified that down by dividing it up into basically a factor pair, but then continuing to divide those into further and further pairs until we got all the way to the lowest ones. So we did like 4 times 21, 21 is 3 times 7, and 4 is 2 times 2. So we come up with a list of prime factors for a number. And finally, you've probably also heard of something called a greatest common factor. You usually learn about it at first with another thing called a least common denominator. And the idea of both of those is that we're looking for a thing that different terms share in common. So the most important thing about what we did with prime factorization is we were dividing out a monomial into its component parts. We only had a single item, not a polynomial. Same thing with the factor pairs. We had a monomial, which was 20, and we split it up into some smaller numbers. A greatest common factor is dealing with a polynomial. So if I have two different numbers, so say 40 and, 66. Then I can find whatever the biggest number that is a factor of both of them is. And I could do that using a factor pair list like over here, or I could do it using the idea of prime factors. So let's prime factor both of these. So I could do 4, 10, 2, 2, 2, 5. And then for this one, I can do 6 and 11, 2 and 3. So looking through my list of prime factors, if I find any that they share, so anything that this one has like this 2 and this 2, that would be a common factor that they share. So both of them have 2 as a factor, but that's the only one. So their greatest common factor is 2. So the GCF of these is just 2. We could pick a number that has more things in common, like say 48 and 72. When we factor those, we can do 4 and 12. We can do 6 and 12. And then 6 is 2 and 3. 4 is 2 and 2. So I didn't factor it all the way down, but the idea is we have a 2 and a 12 and a 2 and a 12, meaning the GCF, the greatest common factor of these two numbers, would be 2 times 12 or 24. And in fact, we can think of this as 48 is 2 times 24 and 72 is 3 times 24. So this 24 that they share is their GCF. So that's our main topic for today that we're going to look at, is the greatest common factor of a polynomial. So remember, we start off talking about distribution here. So we have a times parentheses b plus c. And when we multiply a by both of these, we get ab plus ac. So this is the distributive property. And the two that we end up with, AB and AC, so AB and AC, have a common factor of A. So if we started with AB plus AC and we wanted to go backwards, we could undistribute it by taking the A away from both of those. So one of our main takeaways for today is that factoring is the opposite of distributing or of multiplying. So we saw with the examples with just a single monomial that we were dividing it into smaller pieces. So we were using division to break the number apart. So factoring is like polynomial multiplication, and distributing is polynomial multiplication, and factoring is polynomial division. But they are opposites, just like multiplying and dividing are opposites. So if we start with AB and AC, we have a common factor of A, so we can undistribute to factor out that GCF, resulting in the factored form A times B plus C. So these are dealing with polynomials now, not just monomials. And with polynomials, we factor out a common factor, I guess. A common factor with numbers and variables. So that's another thing we'll talk about here, is that a greatest common factor is not necessarily just numbers. It could also have variables. So there's some steps here. It says to list the factors of each term. You won't have to do this every time once you get familiar with working with the numbers and you just recognize this number and this number share a certain factor. So let's, for this one though, say 6 is made up of 2 and 3. 12 is made up of 2 and 6, which is made up of 2 and 3. So we have a GCF of the numbers of 2 times 3 and 2 times 3, which is 6. So my greatest common factor, GCF, is 6, and that's step 2. Step 3 is to take the 6 and put it outside parentheses so that we are undistributing it. We're taking it away from both things. And then we see what's left behind. So if I have 6x and I take away 6, so divide by 6, I get just x. And if I have this 12 and I take 6 away from it, I divide by 6, I'm left with just this single 2 right here. So we end up with 6 parentheses x plus 2. And if you want to check your work in factoring, you can always just mentally redistribute it. So if I redistribute this, I would get 6x plus 12, and then we can be sure that we are that we have that taken care of. And then there's a note here. We'll see how it works on the next one. It says never leave a leading term inside of the parentheses as a negative. So I'm going to make up a really simple example here so we can see it, and then we'll see it another time or two down below. So if I had something like negative x plus 4, you look at those and say there's no common factors there because this one has a coefficient of 1 and this one is 4 and it has no x's, so there's nothing they have in common. But we still, if we're factoring, we always would bring out a negative to the front and then make this x minus 4. And that part is sometimes confusing because if you think about this plus 4, if I divide by negative 1, so I take a negative 1 outside the parentheses, I would end up with a negative 4. The easiest way, I think, is just to think of, again, redistributing it. So if I distribute this, I would get back negative x plus 4. All right, so we're going to look at some examples in the notes here. The first one does have a leading negative, so we're going to factor out a negative, but also we're going to look for what else do they share in common. So I'm not going to write out the whole factor tree. You can definitely do that if you want to. I'm just going to think of this as 4 times 5 because I can see that they have a 4 in common. And then x squared and x to the first have x in common. So they both, I can divide out an x, and they're both fine with that. So when I take negative 4x, I divide negative 4x squared by this, I'm left with just a single x. So again, think if I redistribute this, I will get negative 4x squared. Then I had a plus, so when I'm distributing back, I need a minus here in order to make the right thing. So if I divide 20x by negative 4x, I just get negative 5. And again, I check by multiplying this back, I get negative 4x times negative 5 is positive 20x. So especially while you're new at this, always do that mental double check of making sure that you end up with the right thing if you multiply it back out. On the second one, our coefficients have nothing in common because 5 is a prime number and it doesn't divide into 9. So the only thing they share is b to the first power. I can take b away from both of these and they're still fine with it. So I'm going to put b outside the parentheses. Then I'm left with a 5 here because b times 5 will create this 5b. And then I divide 9b cubed by b to the first and I get 9b squared. And again, if I check, that times that is 5b, and that times that is 9b cubed. So I get what I wanted. Now we have a trinomial. So with anything, it doesn't matter how many terms there are, they all have to share the same factor as a GCF to take it out. So no matter how many terms we're looking at, we're still looking for every term to share something. So here I can see that 16, 20, and 12 are all divisible by 4 because this is 4 times 4. This is 4 times 5, and this is 4 times 3. If you can't immediately see that, then remember you can always do what we did above and write the little factor tree to find all of the common prime factors and then put them back together. So I find a GCF between all three terms is 4. So I put 4 in front of my parentheses. But I also need to look at my variables. I have x squared, x, but this one has no x's. My constant doesn't have any x's to take away, so it can't have x as a common factor with the other ones. So 4 is our only GCF here, and we'll be left with 4x squared, then minus 5x, and then plus 3. So now if I redistribute, 16x squared minus 20x plus 12, I get exactly what I wanted. Another thing to do after you take out a GCF, so sometimes you don't find the biggest number. So I want to go back and check and make sure there's no GCF of what's left behind. So if there is, then just keep going and factor another thing out. Actually, let's do this one as an example and show what would happen if I didn't start correctly. So I see all of these are even numbers. So let's say I factor out 2. And then I'm left with 8x squared minus 10x plus 6. And I see that all of my coefficients are still even, meaning they're all still divisible by 2. Instead of like throwing away my work and starting over, I'm just going to factor out 2 again. So then I end up with 2 times 2, and I'm left with 4x squared minus 5x plus 3. So if I take out multiple factors, they just combine together by multiplying, and I get to the same end result. So if you notice that you take out a factor that wasn't quite the GCF, that's okay. Just keep going and do the next step and factor more stuff. All right, we have a bunch more examples here and then one other topic, so I'm going to go through these 5. If you understand the concept, I'd like you to pause and go through these 5 and then use my answers to check your work, but do try them on your own. So for the first one, we have to factor out negative 9y squared. We're going to be left with positive 2y plus 1. So this one's a little tricky, but if we multiply back, you'll see everything works out. So negative 9 times this will give us negative 18. Y squared times y is y cubed. And then here we're left with 1. A common mistake is to say, oh, we took away negative 9y squared, so there's nothing left here. And sometimes I'll see the error where we put just 2y and we lose the second term entirely. That's impossible. We can't do that. So we have to make sure that when we divide negative 9y squared by negative 9y squared, we're still left with 1 for this second term of our binomial. Second one, we can't actually factor anything because 9 and 8 have no common factors, or 9 and 8 squared. And d squared, there's no d's over here, so they don't share anything. So this actually can't be factored at all. It's just 9d squared minus 64, but 9 and 64 have nothing in common. The way I think of it, this is made of 3's, right? 3 times 3, and this is made of a bunch of 2's, because 8 is 2 times 2 times 2, and then we're squaring that, but there's no 3's in there, so they don't share anything. So no GCF for this one. Next one, everything's divisible by 4, and this one has no x's, so I can't take any x's away from it. So we have 4x squared plus 4x minus 21. Next one, we have to take out the negative so that we don't leave this in the parentheses. So we have negative 2. We can't take out any x's because, again, there's no x's on our constant term. So we're left with x squared. And then remember, since we factored out a negative, we have to switch all the signs. Just like distributing switches all the signs, factoring switches all the signs too if we take out a negative. So then we have minus 6x and then minus 3. So double checking our work, negative 2x squared, positive 12x, positive 6. Looks good. Last one, we just have 2 again as our GCF. We get 10x squared plus 3x minus 1. And there we go. The other topic we're looking at today is called factoring by grouping, and it's something that actually is leading closer to what we're going to do with quadratics here. So when we do factoring by grouping, we're not going to look for a GCF of everything. If you look at these numbers, you can clearly see that 2 and 3 have no GCF. There's no x's here, so there's no GCF with the variables. So this looks pretty uninteresting at first glance because there's no GCF for everything. But what we're going to do is regroup it. We're going to take the first 2 terms and group them together. Then we're going to look for a GCF of those. So those two, the 2 and 3 have no GCF, but the x's do. So we can factor out an x and be left with 2x plus 3. Then, if this is a problem that's set up well for this method, which they aren't always, right? This is specifically set up to work well with factoring by grouping. The second pair has negative 5 as a common factor. So I have minus 5, and then I'm left with 2x plus 3. So I get x times 2x plus 3 minus 5 times 2x plus 3. Hopefully that looks important to you because these two are the same. And this may look familiar from when we did multiplying polynomials because this was one of the methods of visualizing that double distribution method. So what we could then do is change this into x minus 5 times 2x plus 3. Because double distribution is just distributing the x to both of these and the negative 5 to both of these. When you do that, it looks like this. Normally, we don't write out that step, so we kind of skip straight to just writing out the 4 individual terms, like what we started with here. But technically, this step in the middle is always there. We just don't usually write it in this form because it doesn't really add any value to multiplying. But for undistributing, it's actually really useful. So we end up with a pair of binomials, and we know that for quadratics that can be extremely useful because this tells us where the zeros or the solutions of the quadratic are. So if we were to graph this as a parabola in Desmos, we would find our zeros at 5, 0 and negative 3 over 2, 0. So really useful thing. And you'll see, we'll talk more about linear factors, which is what we call these, a little bit later. But for now, we just want to do some practice with that. So yeah, and a reminder, these are called linear factors because they are a binomial that's x plus or x minus something. So if we thought of those y equals x minus 5 as a line, y equals 2x plus 3 is a line. Okay, so there's some practice for factoring by grouping. There's a really important note below here that no matter what we're doing in factoring, we're going to spend like 7 days on factoring or something. Always look for a GCF before you do any other kind of factoring. It should always be the first thing you do. So we're going to go through some more examples. There's, 9 examples here. I'll go through a couple and then do the thing where I encourage you to pause and do them yourself, or if you feel like you've got it down, just go and work on it on your own. So we're going to group these two and these two. That's going to give us x times x minus 4, and then we factor out a negative 3 from the second set. Because of this negative, we don't leave it inside the parentheses. So that means we're switching our signs, and we get x minus 4. That's good, they match, so we can simplify this to x minus 3 times x minus 4. Next one, we can factor out a 3 as a GCF before starting. So we want to factor out a 3 first, and then look at factoring by grouping what's left. So I'm left with x squared plus 5x minus 4x minus 20. And I'm going to then group these inside the parentheses. So I get 3. I'm going to write a big parentheses, like a square bracket, just to keep things straight. I get x times x plus 5 minus 4 times x plus 5. Then I can do the thing we did here where we group the x minus 4s together and do 3 times x minus 4 times x plus 5. And this looks like something we're used to seeing as a quadratic equation in factored form. So this is our first opportunity to turn a quadratic into a factored form by going backwards. Instead of starting with the zeros or the solutions, we can undo it and get back to what we started with. So I'll go through and write answers to the rest of these to complete the notes, but if you're going to keep watching, then pause it, try these 7 on your own, and then unpause and go through the answers with me. Okay, so this one we're going to factor out x from these two, get x times x plus 8. Then we factor out 4, so plus 4 times x plus 8. These match good, so we can do x plus 4 times x plus 8. On this one, we factor out x, we get x minus 9, then plus 3 times x minus 9, so we get x plus 3 times x minus 9. This one, we get x minus 4 times x plus 7 times x minus 4, so x plus 7 times x minus 4. This one does not have a GCF. I thought it did for a second. So we have two things to take out here, though. We can take out 2x times 4x minus 5, then plus 3 times 4x minus 5. So we get 2x plus 3 times 4x minus 5. These last 4, we have GCFs on each of these, so we can take out a 4 here, a 3 here, and a 2 here from all 4 terms. So I'm just going to go ahead and write the answers for these. Hopefully you've already tried it. So we take out a 4, and then we get x times x minus 2, so x minus 2 is going to be one of our factors. The other one will be x, and then if I have x minus 2 here, I've taken out a negative 12, but we took out 4, so minus 3. 6, yeah, that looks right. Okay, this one we're going to take out a 3. I didn't account for the trouble of doing these in my head before I just said I was going to do that. Okay, so 3, we have x plus 7x, so we can take out an x, and then we're left with x plus 7 when we take x away. And on this one, to be left with x plus 7, we take away 6, but we already have 3 of that, so it's a 2. So we have 14 times 3 is 42, 2x, 9x, 9x is 27, looks good. And then on the last one, we need to take out a 2. Actually, we need to take out a 2x because they all have an x with them. So this one is actually a cubic, and that's fine. We just take out a 2x and then group what's left. So after we take out 2x, we have x squared minus 5x. So that'll be x and then x minus 5. And to be left with x minus 5 here, we had 3x squared, so we're going to need to take out a 3. So we end up with x plus 3 times x minus 5. So that's all of our notes for today. And then we'll continue on factoring by other methods and get a lot deeper into what we can do with factoring beyond GCF. But we're starting this first day just talking about greatest common factors because it's very, very important that we always look for those, no matter what we're doing within factoring.